Okay, welcome everyone to this talk of the FLOW seminar. So FLOW stands for Federated Learning One World Seminar. And today we have Kshitij Patel. He was already previously a speaker on the seminar, but now he has some new exciting results on the convergence theory of local SGD and the role of personalization. And yeah, you can ask questions during the talk. Please raise your hand, or at the end, we can also have a bit of a discussion. And now, Kshitij, the floor is yours to present.
Yeah, thanks, Sebastian. Hi everyone. I'm Kumar Patel. I'm a fifth year PhD student at TTIC. It's a computer science institute based in University of Chicago campus. And today I'm going to talk about the convergence theory for local SGD and the role of personalization. So at any point, if you can't see my screen or hear me, just stop me and I'll try to see if the setup's working well. So today's talk is going to be based on two papers. The first paper is called The Limit and Potential of Local SGD. It's supposed to be presented at the Conference on Learning Theory 2024 in like less than a month from now. And this is joint work with my advisors, Nati Lingzhao, Nirmit at TTIC, Margaret at Stanford, and Sebastian Annerly at CISPA, as well as Ziheng at Peking. And the other work, which would actually comprise the minority of the talk and will appear towards the end of the talk, is about personalization and how it rectifies some of the issues we see with local STD for heterogeneous distributed learning. And this is a paper currently under review. It's joint work with Ling Zhao and my internship collaborators from last summer, Nidham and Ling Zhao. So with that, let's start the talk. So even though this is a flow seminar, let's do a very brief motivation for why we need distributed optimization. So there are several regimes where we need distributed optimization. So when you have data silos, like there are reports by leading consulting agencies that about 39% of highly data-driven organizations, such as Amazon or Google, have about 50 geographically separated data silos each. And these are usually located throughout the globe, like because it's cheaper to put them in different continents. So, all right, that's a very natural reason to do distributed optimization because your data is actually stored in a distributed fashion. Another setting we look at is when you're training these edge devices, something like mobile phones or self-driving cars. And there's been a lot of applications recently, especially in federated learning, where millions of these devices are connected to each other via the models that are being trained for those devices. And one popular example is the G board or the Google board, which if you are an Android user, you might have used. And finally, even if you're not a big corporation or use an Android phone, you might still be training your models on GPUs. And an example which I like to use to elucidate the role of parallelization is that the all famous ChatGPT, if it were trained on a single GPU, it would have taken 355 years. But fortunately, it was trained on 25,000 GPUs, and the training could be successfully done in several days. The upshot of all of this is large-scale distributed optimization is present in our modern machine learning applications. And because it's present, we have to deal with it, and we also have to deal with its challenges. The challenge is unique to large-scale distributed optimization. As years have gone by and machine learning models have become bigger, the data has become more widespread. The number of parallel nodes which are used in distributed optimization have grown exponentially. And secondly, the latency and low bandwidth, which remain pervasive in these settings, require us to pay special attention to the communication that's required for distributed optimization. And as a result, communication is often the bottleneck for parallel runtime. Like imagine this like data silos which are on different parts of the globe. They have to communicate with each other in order to do the distributed optimization. And often that becomes the bottleneck in overall like parallel runtime. So what's this talk about? This talk is about how can we use powerful local computation or access to powerful hardware locally in order to reduce overall communication. And Apple just had their WWDC like in the last 2 days, and they announced that a lot of their AI intelligence now is going to happen on the phone, on the iPhone, as opposed to being on the cloud. They still rely on the cloud AI models for some applications, but they want to move towards a future where a lot of these things can happen on the device because they already have very powerful chips like the M3 chip Apple has on the device. So, okay, how can we leverage powerful local computation to reduce overall complication? To make things a bit more concrete, because it's a theory talk, we'll be talking about a distributed optimization problem where there are M clients or machines, and each client has an objective capital FM, which is a stochastic optimization objective defined using a loss function F and some data Z and a data distribution DM, which is unique to each client. And the problem we want to solve is the average optimization problem, where we average these clients' objectives and get an average objective capital F. This is a very well studied problem, and all the three problems which I talked about before can in one way or the other be cast into a problem of this sort. One key thing to note about this problem, which would become important when we talk about personalization, is that here we insist on using a single model V for all the devices or all the clients M. All right. So in this model, usually people, when looking at stochastic optimization, consider a simple Oracle access model where at each time step T, each machine has access to a single sample, or you can think of a batch of samples from the distribution, and they can compute the gradient at the sample. And this is very familiar to people perhaps who've done distributed training on multiple GPUs, because at each time T, basically you sample a point from your finite data set and then just compute its gradient or the mini batch gradient using the GPUs. All right. Another important aspect, because we'd be focusing much on communication complexity, is how this computation is distributed across devices and across communication routes. So we have M machines. They all initialize at some point with some model at time T equals to 0. And then they're allowed to do some local computation for K local updates or K local steps. Okay. At this point, they communicate again and synchronize their models in some way. Different algorithms have different takes on how to synchronize their models. And they again get to the phase of local updates. And this goes on and on and on. What we'd be more interested in this talk is the setting where K or the local updates are very large so that we can reduce the overall communication complexity of distributed optimization. This setting is usually called intermittent communication. And you can already imagine there are other settings where K is not held a constant across communication rounds and blah, blah, blah. But I claim that this is the most important setting. And while simple, it offers some interesting perspectives on distributed optimization. Okay, so the most generic algorithm which you can implement in this setting is mini batch SGD. So let me describe mini batch SGD in this setting. So for each machine and each local step, you do the following. You first sample a data point ZRKM from the machine's distribution, and then you compute the gradient at the model corresponding to the previous communication round. So if VR-1 is the model from the previous communication round, you compute the gradient on this sample at this model on the machine. And you keep aggregating these gradients across machines and local steps. And finally, you make a single update by averaging these gradients across the machines. So if you've thought about mini batch SGD before, then this is very akin to how you would implement mini batch SGD. The only catch is that this is equivalent to mini batch SGD with our updates and a batch size of KM as opposed to a batch size of M, because we want to capture the effect of local updates. So you can think of capital K as, in some sense, the batch size which you give to each machine. This variant of mini batch SGD is theoretically called large mini batch SGD, where the word large corresponds to the capital K being large in the overall batch size. Okay, so this is a generic algorithm. This algorithm has been subject of study for the last 5 to 10 years. And perhaps one of the most famous papers which tried to understand large mini batch SGD is in the context of using it to train ImageNet in 1 hour. And in this paper, they showed that they could indeed train ImageNet in 1 hour, which at the time was a big accomplishment. And they also showed that as you increase the mini batch size, there's a point at which you don't see speed ups. And in fact, like increasing the mini batch size too much can lead to poor validation performance. So there are limits to how much you can squeeze out of local computation when you're relying solely on large mini-batch SGD. This has resulted in other alternative algorithms which can more effectively use local computation power. And one such algorithm is local SGD. So local SGD in the same setup can be described as follows. So before each communication round, each machine's local iterate is still initialized at the last synchronized model, which is VR minus 1. Okay, so far so good. Then for each local update, you sample a data point on the machine. All right. You compute the gradient, which is also all right. It's the same as before. But here's the difference. Now, instead of aggregating these gradients, you actually run a single SGD step. So what does this do? This basically runs M independent SGD steps on M different machines, and these trajectories evolve independently because between communication rounds, these samples on different machines are sampled independently. So what happens at the communication round, you may ask? The most naive thing to do is just average these iterates after these local updates. And you keep doing this for our communication rounds and finally update the final consensus model. You could do more clever things like use an inner outer step size, but I'd not get to that in the talk. Although most of our results do apply to that variant of local SGD. So put things into perspective, what's the main difference between local SGD and mini-batch SGD? Well, mini-batch SGD computes the gradients at the same point between communication rounds, while local SGD does not. In other words, local SGD maintains independent sequences of SGD iterates on each machine between communication rounds, and then averages them at the communication round to proceed further. And you might ask, why would I want to do that? Why is that presumably a better way to use local computation? And the simplest example to think about it is if you didn't have any noise, if you were indeed able to sample the same point, or let's say all the points from this distribution which have like non-zero measure or non-zero probability of being sampled, then mini-batch is actually calculating redundant gradients because it keeps calculating the same gradient at the same point throughout the communication round. Mini-batch is only useful when there is new information on samples, right? So at least in the large batch settings or in the settings where noise is very low, it seems that mini-batch is doing wasteful work while computing gradients. On the other hand, local SGD is actually making progress between communication rounds as well. And this is precisely why people think local SGD can be expected to use this local computation more effectively. Because as I showed you in the previous plots, we are most interested in settings where the batch size is large or K is large. And we want to squeeze as much computation out of our local compute as possible. And to give you a bit of historical perspective, local SGD has actually emerged several times in the optimization and learning literature. And maybe the earliest reference to this algorithm is through what people call model averaging. In the optimization literature, it appeared as Polyak-Rupert averaging in 90s, where it's a very simple algorithm. You run independent sequences of SGD, and then you just average them once in the end. So once in the end is the catch here, because as opposed to what local SGD does, which is it repeats the training again and again, even after synchronization, model averaging in 90s just reduced to using it once. In learning theory, there was like similar work, which you might have heard about, which is called bagging. It's a popular ensembling technique called bootstrap aggregation. And it also does something very similar to model aggregation. Local SGD, as we know it now and as we use it now, emerged in this 2017 work by Brendan McMahon at Google, where he tried to show that when you are actually optimizing on decentralized data, like many of the Google's applications require you to do, then having several of these local update steps followed by communication and repeating them over several time steps is the efficient thing to do. And they had some empirical evidence to show that this is actually the right thing to do. Ever since that, local SGD has almost become synonymous with federated learning, which is why often people also call it federated averaging, which is like the federated version of model averaging that appears in the 90s. And in one of our old works, like with Sebastian and Tao and Martin, when I was at EPFL, we actually empirically found that when you increase the number of workers, then it's actually a much better payoff to use local SGD as opposed to mini batch SGD when you're trying to reduce your communication complexity or just trying to reduce, let's say, your time to reach a particular accuracy. This pink line is with several local updates. The blue line is with no local updates. And of course, having too many local updates also hurts, but there's a sweet point as to how many local updates you want to do. As such, to elucidate and understand this effectiveness of local SGD, there's been more than a decade of theoretical work in optimization, starting from this paper in 2009. And one of the important papers here is by Sebastian himself in 2018, where he showed some interesting convergence results about local SGD and how it can actually beat mini batch SGD in some regime. Unfortunately, and this is the point where this work is motivated, most of the existing work is actually unable to show the effectiveness of local SGD over mini batch SGD in any interesting regime with data heterogeneity. And when I say interesting regime, I mean to say that most of these works, even when they are able to show a benefit of local SGD, have to rely on extremely stringent data heterogeneity assumptions, which would become clearer as we go on. And recently, other people, including a group of researchers from CMU, Google, UT Austin, have also tried to explain the effectiveness of local SGD and something they appropriately term as the unreasonable effectiveness of federated averaging when you have data heterogeneity. And like us, they have been also motivated by how the existing data heterogeneity assumptions are too stringent and might not be painting an accurate picture for when local SGD is effective. All right, so that's the motivation. Let's now jump into what these data heterogeneity assumptions are actually. And I'd be using a very simple running example throughout the talk to elucidate what data heterogeneity is and how local SGD might perform on tasks with data heterogeneity. So this is the example. It's a very simple distributed least square regression problem. Each machine has Gaussian features. So you're sampling from some Gaussian distribution with mean mu m and covariance matrix sigma m. And each machine's label is generated as VM star inner product with this X plus some noise. So you can say that the ground truth model for each machine is well specified. It's VM star. So what does this do? This two-step procedure actually defines a distribution on the X, Y pairs or the covariate label pairs on the data. All right. And what's the cost function for each machine? The cost function is simple squared error. So you're just looking at how much of a linear model is when it's trying to predict using X, what the Y is. And the linear model makes sense here because you're actually using the ground truth in a linear way. All right. So if you take the expectation over these randomness, then you can actually write this objective for each machine as a quadratic optimization problem, where the Hessian matrix is determined by the means in the covariance matrix of each machines, and each machine is minimized at VM star. And there's some constant term, which we don't care much about. So what do existing data heterogeneity assumptions do? And there are many of those. I am going to talk about only one of those, which I think is quite representative of most of them. So most existing data heterogeneity assumptions try to control the client drift between communication routes. In other words, it tries to control how far do the clients go to each other between communication routes. And perhaps the simplest way to do that is by assuming that the gradients on the clients are pointwise uniformly closed. So what does this assumption say? Let's pass this assumption. So taking a supremum over all the machines and over all the models, we want to control how far is the gradient of machine M from the average gradient. And we want to bound it with a constant zeta squared. So why is the gradient the quantity that controls the client drift? Because we are basically looking at gradient descent style algorithms. And thus, if we can control how different do the gradients look, we can also control how different do the iterate sequences look. This assumption is extremely restrictive, and let me tell you why. So if we assume zeta is less than infinity, which we would want to do for any understanding of this problem class, then it actually implies that there is zero feature heterogeneity, or the Hessians across the machines, across the objectives have to be the same. Mathematically, zeta less than infinity implies that the Hessians, which I pointed to before in our distributed linear regression example, have to be the same. And this, I claim, is pretty restrictive because this allows for very little feature heterogeneity, or how the x's are distributed across the machines. Unfortunately, as restricted as this assumption is, this is the only known assumption where local SGD can provably beat mini-batch SGD. And the catch is there are other assumptions under which local SGD has been analyzed, but assumptions under which local SGD can provably beat mini-batch SGD, this is perhaps the only assumption which we have in practice right now. Okay. So the paper I mentioned before, which is this unreasonable effectiveness of federated averaging paper, they actually argued that this assumption is not only restrictive, but it's actually misleading. It's misleading because when you look at the analysis of local SGD that go through this assumption, they actually imply an upper bound on the client drift, which is much more pessimistic than what you actually see on actual data sets where federated learning is usually benchmarked, like feminist and Stack Overflow. So this blue thing is the upper bound, the red quantity is roughly what we want to control. And they show that these upper bounds are kind of loose, implying that this assumption is too restrictive, misleading, and it's actually mischaracterizing the class of problems which we can feasibly solve. Okay, so what can we do? How do we relax this assumption? So before relaxing this assumption, let me actually show you what data heterogeneity actually corresponds to in the distributed linear regression example we are referring to. So one can imagine two kinds of distribution shifts happening between the machines here. The first kind is where you're controlling y given x across the machines. So given the data, how am I going to label the data? And you already know that the ground truth VM star controls this. So assuming the average of VM stars is denoted by V bar star, we can control this concept shift by controlling the heterogeneity across VM stars, or the variance across VM stars. Okay, so if we assume this quantity is small, then y given x, the distribution shift caused by that, is also going to be small. The other kind of shift, which I already talked about, is covariate or feature shift, where the x distributions are actually going to vary across the machines. But again, in our example, we can easily control them by either controlling the mean of the covariates or the covariance matrices of the covariates. In general, you might not have one of these distribution shifts, but both of them, or some mixture of both of these shifts. And why I'm trying to present this model is because I think this is a good model to study what happens in practice when we are dealing with the actual data set where federated learning is to be deployed. We can try to understand what's high. Is it the covariate shift or the concept shift? And accordingly switch our algorithm. Okay. So what kind of data heterogeneity assumptions are actually implied by these two distribution shifts? So let's look at our quadratic optimization problem from before and abstract it a little more to ease the notation. So instead of using the mu transport plus sigma m I had before, let's denote that by a Hessian matrix AM, which we assume is positive definite and has smallest and largest eigenvalues bounded by mu and h. All right. We also assume that instead of sampling from the distribution, we somehow have access to an abstract model of first order information, which gives you unbiased information about the gradients at a point. And these oracles, first order oracles, are actually also bounded in variance. So there's a variance bound and these are unbiased. All right, standard assumptions. So let's first look at the issue of concept shift, or y given x. So we'll denote the set of optima of each objective by Sm star and the set of optima of the average objective by S star. And then we'll assume that each of the optimas across the machines are bounded. We don't want anything to go to infinity to have weird pathologies there. We can note two things about how these sets Sm star and S star relate to each other. First, the intersection of the optima of all the machines is actually a subset of the optima of the average objective. What's this saying in words? It's saying that if I can optimize each machine's objective with some model, then that in particular also optimizes the average objective because each summand of the sum is actually optimized. We can also note that whenever this set is non-empty, whenever there's a shared optimum between the machines, then actually that shared set of optima is the set of optima of the average objective. Because if there were any other objective which does not lie in this intersection, that's probably going to be worse for the average objective as well. So if we have shared optimum, what happens to our concept shift? If there's a shared optimum, then there actually exists some optima for which VM stars are all the same, which means that this quantity is 0. So the upshot is having shared optimum implies that the label shift or the concept shift can be reduced to 0. So that's a very intuitive and easy problem class we might want to understand. And the question we can ask is for this class, how quickly can local SGD recover a shared optimum? All right, so is the question clear? So we want to understand that when we don't have any concept shift, maybe we do have feature shift still, how can local SGD, how quickly can it recover a shared optimum? And this is our first low bound. We show that there exists a quadratic problem instance, which is actually general convex. So the smallest eigenvalue is 0, such that local SGD iterate with any step size eta initialized at 0 has the following lower bound on convergence. Now, this lower bound has 3 terms. This is the optimization term, this is the noise term, and this is again some mixture of optimization and noise terms. But the important thing to note about this convergence guarantee is that even if I squeeze my local computation as much as possible, even if I send k to infinity, I cannot reduce the first term. Like I cannot get rid of this optimization term without taking communication rounds to infinity, which is opposite of what I want to do because I want to minimize the communication while squeezing as much as possible out of the local compute. So what this implies in words is that local SGD cannot converge to the shared optimum of the clients, even if there is one with finite communication. So to highlight that there is indeed a shared optimum in this quadratic problem, it's just that local SGD cannot converge to it with finite communication. So this is bad. We can ask, can the optimal algorithm also converge to this optimum with finite communication? Turns out the answer is no. And the optimum algorithm for this is characterized using another lower bound, which applies not only to local SGD, but to all class of distributed zero respecting algorithms. It's a technical definition, but what you can think of is it's a general enough definition which encompasses mini batch SGD, local SGD, maybe some variance reduce algorithms you might want to look at, things like scaffold, and anything else you might presumably imagine to do with like first order information. And what this shows is that the optimal algorithm is actually accelerated mini batch of SGD. So it's not accelerated local SGD, it's actually accelerated mini batch SGD. And all right, we give this lower bound. And again, this lower bound does not go to 0 when k goes to infinity. So far, we've characterized the min-max optimal algorithm for the class of problems which do have a shared optimum. And these are convex smooth problems. We've shown that local SGD cannot do well with finite communication. And in fact, no algorithm can do well with finite communication. If there are any questions here, we can stop here for a moment and take questions. Otherwise, I'll keep going. All right.
Yeah, does not seem to be the case. So let's let's go on.
So let me give you the motivating example for proving this low bound. And it's a very simple example, although we have to get into a few more technicalities to prove the actual low bound, but this is a good motivating example. So consider 2 machines and consider a 2-dimensional problem. The first machine has its objective given by, okay, it's just a scalar objective which only depends on the first coordinate. And the optimizer of the machine is x star 1. It's a scalar. And on the second dimension, you can put anything. Like the machine doesn't care what you put on the second dimension. Similarly, for the second machine, you have the same thing, but for the second dimension, like the optimizer is x star 2, and it doesn't care what you put on the first dimension. And when you average these objectives, you just get a strongly convex objective, which looks like this, where the optimizer is a singleton point x star. Okay, so clearly there is a shared optimum between the machines, because on one hand, all the first machine, all the optimizers are on a line, with the first coordinate being x star 1. For the second machine, all the optimizers are on a line with the second coordinate being x star 2. And the intersection is this singleton point x star. So clearly there's an example with a shared optimum. What ends up happening, as you might already see, is that when k goes to infinity with initialization at 0, then after one communication round, we'll recover x star over 2, not x star. In the second round, we'll recover 3x star over 4, 7x star over 8. And you can see there's an exponential kind of recovery happening of x star, but it requires r to be infinity. And this is even with k going to infinity. So what are we seeing? We're seeing that because these machines have no information about the other dimension, like the first machine doesn't know anything about the second dimension, the second machine doesn't know anything about the first dimension, they cannot really leverage local work very well between communication terms. And there's a very simplistic example. You might think, oh, okay, if I improve my algorithm, this seems like just a scale problem. What if I multiply everything by 2? Maybe that will make my algorithm better. And you can try to do those kinds of things. You can consider local SGD with inner outer step sizes. You can look at other algorithms like scaffold, blah, blah, blah. But the actual construction in our paper, which generalizes the simple idea, will still make it such that the lower bound would apply to our algorithm. So this is a fundamental hardness that we are looking at. And the hardness is essentially something I'll get back to later, which is what do you do when you don't have information about all the dimensions on each machines? And this is a real problem, because often you want to train models collaboratively where one user or one agent has some information about the data set, which the other user doesn't, and so on and so forth. Like, how do you combine information effectively in such a setting? So that's all I'll say about this lower bound, but there's a full proof in the paper if you guys are interested. Okay, so we'll get back to this issue of different information on different machines later. But before we do that, let me show you another implication of our lower bound. So I talked about the assumption A1, which is bounding the gradients across the machines uniformly over the entire domain RT. And people considered another relaxation of that assumption. And people have been looking at such relaxations for a while because they knew that that assumption in particular is very restrictive. And one simple relaxation which people have looked at is instead of assuming that the gradients are actually close pointwise on the entire domain, we only assume that the gradients are small for every point which optimizes the average objective, for every point which is in S star. So this assumption, which we'll call A2, just has this first order bounded gradient heterogeneity at the optima of the average objective. Okay, so how does this relate to what we've talked about so far? The first thing is that if zeta star is 0, it implies that there is indeed a shared optimum between the clients, because the intersection of all SM stars has to be non-zero and it has to be equal to S star in that setting, right? And even when zeta star is not 0, it intuitively captures the concept shift, which I talked about. So when you go from the setting of having shared optimum to having not shared optimum, but optimum which are close enough to being shared, then you have non-zero concept shift. And our lower bound actually characterizes tight convergence rate for local SGD under this assumption. In particular, we show this convergence rate. So this convergence rate, this has a big theta here. The lower bound is implied by our result, and the upper bound is implied by another work by Anastasia and Sebastian from 2020, where they looked at the zeta star assumption and tried to analyze local SGD. So you can get this convergence rate for local SGD. But again, as you might see, as k goes to infinity, you cannot really drive the optimization term to 0. So even when zeta star is small, even when data heterogeneity is presumably small, you still have to pay the price of not communicating because of this term. And to make the contrast even clear, if you were indeed looking at the zeta assumption, which implies that the gradients are close on the entire domain, then you can leverage local computation very well. Because here, when you send k to infinity and when your zeta is a small, everything can go to 0. And you can actually get arbitrarily close to the model you're trying to recover with presumably finite communication. Okay, so we already knew A1 is a nice assumption, but now because of our lower bound, we know that A2 is not a good assumption because it does not provide enough control on data heterogeneity for local SGD to benefit from it. All right. So one might ask, so far we've seen the set of shared optima, we've seen a generalization of the assumption of shared optima using assumption A2, and both of these do not seem to be enough. Both of these do not seem to be sufficient to prove a benefit of local SGD. On the other hand, we have the assumption A1, which is indeed sufficient. So we can ask, is there an alternate relaxation of the zeta assumption or A1 in another, perhaps more reasonable way, which also retains the benefit of local update steps? With this, I'm going to go back to the issue of different Hessians that I mentioned before. So if you might, if you remember, like in the motivating example for the lower bounds, I actually used the fact that the Hessians on the different machines are different because the first machine doesn't know anything about the second coordinate, second machine doesn't know anything about the first coordinate. So let's look at the Hessians in our distributed least square regression example. So if I write this kind of thing, this is a spectral norm, then I can actually bound the distance between the Hessians in terms of the means of different machines and the covariance matrices of different machines. Okay, this is intuitively making sense because, okay, if both the means and covariance matrices are close, then of course this quantity would also be close to 0. The upshot is if you bound the covariate shifts, which are these things control how the features across the machines differ, then you in turn end up bounding the Hessian dissimilarity between the machines. This motivates another assumption, A3, which is implicitly assuming that this Hessian dissimilarity is bounded by something like tau. And while it does away with the fine-grained detail of mu and sigma, it provides a good abstract model to try to understand convergence of local SGD. So can we actually do better if we somehow use this assumption in addition to the other assumptions? One thing is clear, like if I force tau to go to 0, then I cannot use the motivating example I used in the previous slide. But what does the lower bound reduce to in this setting? This assumption, okay, so just to recall, this was the problem I had shown you before, the motivating example. And if I send tau to 0, then I cannot use this motivating example because the Hessians are not the same even when tau is 0 for this example. So I have to either scale the whole example by tau or something of that sort. But if I do that, of course, I lose the benefit of the lower bound. So what can I do? This assumption of tau or second order heterogeneity, as many papers have called it, was recently shown useful in the non-convex setting to understand local optimization algorithms. And it turns out that it's actually also useful in the convex setting. So this is our lower bound when you have assumption on the second order heterogeneity. And let's say you also have shared optimums or zeta star is 0. Previously, we showed that if you have a shared optimum, and that's pretty much it, then you cannot benefit from local work because there was this term with HB square over R. But now if you make an assumption on relating the Hessians of different machines, then you can presumably benefit from local work. How so? So when tau is small, when second order heterogeneity is small, now you see that sending k to infinity takes each of these terms to 0, which means that when tau is small, there's indeed a possibility that I might be able to benefit from large k and actually get to a good solution in finite communication rounds. Can we match this lower bound? Or is this a loose lower bound? That's an open problem. I don't yet know if it's possible to match it or improve it. But we make some progress towards understanding this problem under this assumption. In particular, we show the following upper bound for local SGD when we make the tau assumption, which is A3, and the zeta assumption. And this is a bit unsatisfactory because I'm looking at the zeta assumption after saying that it's a bad assumption for like 15 minutes. But so far, we only know how to give this upper bound in terms of the zeta assumption and not the zeta star assumption, which would be more ideal. But okay, what do we get in terms of the zeta assumption? We get an improved convergence guarantee, which is even better than the convergence guarantee offered by Woodworth et al. Because when tau is small or the second order heterogeneity is small, we can make these last two terms much smaller than what Woodworth et al. Could do. In particular, when tau is approaching 0, then we get only first two terms, which go to 0 when k goes to infinity and r is held constant. In particular, this shows that tau, or the second order heterogeneity assumption, in conjunction with the first order heterogeneity assumption, is extremely useful for understanding local SGD and might exactly be behind what controls the benefit of local update steps. Okay, so another open question is replacing zeta with zeta star or showing that it's not possible in this setting. And we leave that to future work. So to summarize what I've said so far, and also give you a little more perspective on understanding the min-max optimal algorithms here, when we are looking at the problems, quadratic problems in particular, which do contain the distributed least square regression example I mentioned, then we already understand that when we are in the homogeneous setting or where all the distribution across the machines are the same, then local SGD is optimal. That's known since the last like 4 or 5 years at least. But what we showed is that if we are even slightly above this setting of homogeneity, which is to say that, okay, now the distributions are not the same, but we do have some shared optima, then there's this lower bound, which is in this square that we mentioned, which actually prohibits local SGD from benefiting over mini-batch SGD. And in fact, up to acceleration, mini-batch SGD is optimal in this setting. We also showed that we can remove this lower bound or at least reduce the effect of this pathology of local SGD by considering the bounded Hessian dissimilarity. This is the upper bound I just showed you on the previous slide. Now I'll actually go to the next slide and try to understand that we can do even better if we consider strong convexity along with all these existing assumptions. So strong convexity in addition to first and second order heterogeneity can offer even deeper insights about the utility of local optimization. And this brings me to the same problem which we had before, which is this quadratic problem. We're going to assume that it's like strictly convex now. So it's not convex, it's strongly convex now. Mu is strongly convex in particular. And because it's such a simple problem, we can write in closed form the equation for what's the optimizer for the average function, as well as what is the average of the optimizers. So V star is the optimizer of the average function, and V bar star is the average of the optimizers of different objectives. These two objects are actually different. And they are not only different, the distance between these 2 points is actually controlled by the assumptions we've looked at, which are the zeta star and tau assumption, the first and second order heterogeneity assumptions, as well as the smoothness and strong convexity assumption. Like to give you a graphical illustration of this, if you have like these 5 quadratic problems, I look at the convex hull defined by these problems, then both V bar star and V star lie inside this convex hull, and their distance is controlled by data heterogeneity, zeta star and tau. But why am I talking about V star and V bar star? V star maybe makes sense because we want to converge to V star. Why am I talking about V bar star? So the reason I'm talking about the average of the optimizers of different machines in the strongly convex setting is because we'll soon see that local SGD might actually converge to V bar star when K is very large or local optimization is very high. It turns out that we can explicitly write the convergence point for local gradient descent without noise. And all of this discussion is going to be without noise in this setting. And I'll not bore you with the exact form of the fixed point of local gradient descent, but I'd like to show you this figure where I've basically zoomed into this part of the problem. So I've zoomed on this line segment between V bar star and V star. And when I do that, then I see a very interesting phenomenon. When I use a large step size zeta, a step size which does not depend on 1 over k or 1 over local steps, then actually I never converge to V star. I converge to V bar star as I increase my local computation or local work. But if I allow a smaller step size, which actually decays linearly or even quadratically with k, then I can force local SGD to converge to V star, which is the point I actually want to recover. And this is interesting, but not so surprising if you think about it. Because if you make the step size small, then you're actually getting closer and closer to using mini batch SGD. Because when you make the step size small, your client drift between the communication rounds is so small that you're effectively computing the gradients at the same point. In particular, the relevant scale depends on k here because moving from here to here, we are actually taking k to infinity. And if your step size also decays accordingly, then even when you take k to infinity, you do not hover much further from the fixed point you want to recover, which is V star. But if you do that, if you set your step size to something constant, then you actually go much further away from V star all the way up to V bar star. And these are actually two opposite forces here. On one hand, using a large inner step size will make convergence quick because I'll optimize more quickly. I'll need less communication rounds. But on the other hand, making the inner step size large would also mean that the fixed point discrepancy increases. In other words, I'm going to hover much further away from the point I actually want to recover and go to some other random point which I don't really care about. And it turns out that we can combine the previous idea to give another convergence rate for local STD and more accurately local GD in this setting because there's no noise here, which looks as follows. So with assumptions on second and first order heterogeneity, tau and zeta star, we can actually show that the local gradient descent convergence depends on two terms. The first term is this optimization term, which is very fast. With the large K, you can make this very small and even counteract the effect of having a poorly conditioned problem. But the other term, which is the fixed point discrepancy, actually does not improve with K or even with R. It is something you have to pay for if you're using a large inner step size. But at least what this tells us that when tau and zeta star both are small, or in other words, when both the concept shift and the feature shift of my data distributions is small, then I can actually get away with near constant communication complexity. All right. But this might motivate the next important question. Can we remove this fixed point discrepancy altogether? Can we get rid of the second term? Turns out we can, not by using a consensus model, which local STD does, but by using personalization. And this is going to be the last part of the talk. So let's revisit this fixed point discrepancy in another example. So you have two quadratic problems that you're trying to optimize. This is the optimum of the first problem. This is the optimum of the second problem. And this is the optimum of the average objective. Now, what local STD does is these are the trajectories of two machines. So between local steps, the trajectories diverge because each machine is going to try to approximately recover its own point. The first machine is trying to get to V1 star, second machine is trying to get to V2 star. But every time I communicate, I bring them back to a point which is something else altogether. And this keeps on going, like this oscillation keeps on going, like the machines diverge and then I bring them together. The machines diverge and I bring them together. To the extent that when I'm approaching V star, at that point, these oscillations cost me because even when I am close to V star, the machines now want to get away from V star because the first machine is trying to go to V1 star, the second machine is trying to go to V2 star, which results in this weird fixed point discrepancy that we talked about. If it were the case that either zeta star were zero, which is to say V1 star equals to V star or V2 star, there wouldn't be any such discrepancy. Or if it were the case that the covariate shift were small, then again, there wouldn't be any fixed point discrepancy. But in real data sets, there is actually a fixed point discrepancy. So how do we remove it? This is where the magic of personalization kicks in. Can you still hear me? Okay. So the magic of personalization is that now instead of trying to force my model to converge to V star, which is the optimizer of the average objective. Okay, there's something wrong with my video. Let me turn off my video. As long as you can still hear me, that's fine. Okay, so what personalization does is that instead of forcing the algorithm to converge to some point, which is not even its fixed point, it actually allows you to individually recover both V1 star and V2 star, while at the same time benefiting from collaboration. Because benefiting from collaboration is key here. I can always recover V1 star and V2 star by doing pure independent local training on each machine. What's interesting is whether I can recover them while benefiting from collaboration in some way. And to give you a sense of what kind of guarantee we can get with personalization, we'll look at this kind of objective, which is even harder than the objective we've been looking at so far, where each machine is being compared not against V star, which is the average objectives optimizer, but it's being compared against the optimizer of machine M VM star. So this is much harder than the previous objective or the non-personalized objective, because this can be much, much larger than the previous objective. In particular, it could be the case that the second term is close to 0 and the first term is very large. While if you insist on using a consensus model like V star, then this could be as high as order zeta star square. So this is a harder objective. It's a harder problem, but you can still insist on using local SGD because, well, local SGD is one way to solve this problem by insisting on using the same VM across the machines, right? So it turns out that personalized local SGD, which I showed you in this particular example, makes a very simple modification to the local SGD algorithm, which gets rid of this fixed point discrepancy. So what's that modification? So again, for each communication round, some of the things are going to look similar. So on each machine, for each communication round, for each local update, we sample a data point. We compute the gradient. Everything is same so far. But now instead of making an update on the model V, we make two kinds of updates. First, we update what I call the shared model, W, with this gradient. And then I update the personal model, which I call theta, with this gradient. The gradient is the same, but I'm updating them differently because in one case, I'm scaling it by eta. In the other, I'm scaling it by alpha times eta. Okay. Now, how do I combine these shared and personal models? Basically, to combine them, I just add them. As simple as it could get. And at the communication round, I only average the shared model because intuitively, this is capturing the shared component of collaboration. This is capturing the aspect of basically the model, which is presumably similar across the machines and should benefit from collaboration, while this other term is capturing something which is personal to that machine. And this alpha parameter is actually extremely relevant when it comes to removing the fixed point discrepancy. Because now when you look at the fixed point of this algorithm or fixed points of this algorithm, it is no longer V star or the optimizer of the average objective, but it is actually the optimizer of each machine separately. Because of this addition of theta, now I can force the trajectories of different machines to not go to V star, but instead go to V1 star and V2 star respectively. And this is a much cleaner problem because now I'm actually solving the problem I want to solve, which is the personalized federated learning problem. And my fixed point respects the problem that I'm trying to solve. There is no fixed point discrepancy. So turns out this is extremely useful when I'm trying to look at the convergence guarantees. And if we look at a mean estimation problem, so this is a simple quadratic optimization problem where the Hessians are shared across the machines. All I'm trying to do is estimate some Gaussian mean on each machine where the variance is also shared. A very simple problem. This is in some sense the easiest optimization problem that one can solve, which is also hard at the same time because it elucidates the benefits of collaboration. So, okay, you could of course also solve linear problems, but linear problems in a stochastic setting are trivial. So this is the easiest quadratic problem you can solve. It turns out that when you make the zeta star assumption in this setting, because that controls is still the concept shift. The concept shift is just the heterogeneity of the means here. Then with personalization versus without personalization, there's a huge gap between the convergence guarantees. Without personalization, you always have to pay this price in terms of zeta star, which comes from basically insisting on using a single consensus model or the local SGD model for each machine. But with personalization, you can actually drive this thing to zero with more and more communication. And not only you can do that with more communication, you can do that exponentially quickly with more communication. So with personalization, you can actually get rid of heterogeneity altogether. As you get closer and closer to convergence, you can actually recover the true solutions of the machines, because that's what the objective on the left captures. And somehow heterogeneity doesn't matter. And this captures very much the intuition we had about local SGD, which is that far away from optimization, you should somehow be okay with using local SGD. But when you get closer to the optima, then either you need to do something to deal with this fixed point discrepancy. And what personalization does is it introduces this parameter theta, which gets away with this fixed point discrepancy. This is exactly what's happening in this figure. The fixed point discrepancy, or the confusion which local SGD had at the point V star, is somehow we're getting rid of that confusion now. We can extend this to beyond mean estimation, but I think I'm running a little out of time, so I'll not go over the exact guarantee. This is a guarantee for general strongly convex functions. It looks a bit complicated, but if we look at the setting of large K, then it again simplifies to two terms. The first term falls exponentially quickly with communication, and the second term is like a usual noise term. And we do benefit from collaboration. Like, the upshot of this result is that not only do we reduce the heterogeneity term, but we benefit from collaboration. Which, if I go back to the mean estimation example, we can see that the first term actually matches pure local training, but the noise term is much better than pure local training when M is large. So what this shows you is that you do get the benefit of noise reduction without paying the price for heterogeneity, and as quick optimization as possible with pure local training. So this algorithm is better than both pure local training and local SGD with a consensus model. And we did some preliminary experiments to try to understand how heterogeneity affects this. So the red line here is personalized local SGD. The green line is local SGD. The orange line is large mini batch SGD. And the blue line is pure local training. And I'm looking at the personalized federated learning objective here. And on each plot, when going from left to right, I'm actually increasing the y given x heterogeneity. While going between the plots, I'm increasing the heterogeneity in the data distributions x. And what we see is that across these settings, personalized local SGD does much better than all the other algorithms, except when the heterogeneity is very high, because then pure local training is presumably as good as personalization. So that's pretty much it. To conclude, we showed analysis in distributed optimization for quadratic problems in this talk, but most of our lower bounds apply to the convex settings. Most of our upper bounds also extend to beyond quadratic settings with assumptions such as third order smoothness. So far, we've not been able to carry over the fixed point based analysis to the convex setting, because the fixed points don't have a simple closed form in that setting. And as I've highlighted throughout the talk, there are still gaps between upper and lower bounds in some of our analysis. And what I would like you to take away from this talk is that there's still exciting directions. There's still interesting problems when we are trying to understand data heterogeneity for collaborative learning problems. And based on my perspective on studying both local SGD and personalization, I think the future work should focus on characterizing three important regimes which are interpretable, let's say in terms of known distribution shift concepts like concept and covariate shift. And at the same time, they demarcate three regimes: a low heterogeneity regime, where whatever we've been doing with federated learning works, where using a consensus model works. This is the first 80% of the talk. an intermediate heterogeneity regime where we can benefit from collaboration, but we have to be smart about it because there are things like fixed point discrepancy. So we might want to use something like personalization. And then there's a high heterogeneity regime where we might as well benefit from not collaborating, because I ignored something in this talk, which is that there's a cost to collaborating, the privacy cost, the communication cost. So there is indeed a setting where you might not want to collaborate. And understanding these three regimes theoretically is an important future work. And finally, in terms of where this talk started with, where does that leave us with respect to local update methods or getting most out of our local optimization methods? There are several interesting things which, in my opinion, have emerged in the past 2 years literature. The first is that perhaps the first few series of works which looked at client drift were much more pessimistic about client drift than they needed to be, because actually client drift doesn't hurt local SGD so much as long as there is no fixed point discrepancy. As long as everyone's roughly converging to the same place, you're fine with having some client drift. The real culprit is the fixed point discrepancy, which is largely at play when using local updates. And in future, we might want to design smarter multi-stage algorithms or personalized algorithms to get rid of this. Strong convexity is central to avoiding the pathologies where local updates might cause irrecoverable drifts. But of course, we can't only solve strongly convex problems. We have to solve non-convex, harder problems. So we need to derive better algorithms which can go beyond strong convexity. Conditioning, which a lot of papers have shown, is primarily where the benefit of local work comes. I believe is going to be even more interesting. And I'm starting to believe that collaboration is actually acting as a regularizer when it comes to poorly conditioned problems, or at least some of the machines being poorly conditioned. And finally, it remains to be seen which of these distribution shifts, concept of feature shifts, would be interesting as we start to actually take this theory closer to more applied algorithms for collaborative learning. With that, I'll end. And if you have more questions, I'm happy to answer. And thanks a lot.
Okay, thanks, Kshitij. Many thanks for the talk. It was, very good, a bit, on the longer end. So if people have to leave, say thanks for joining, and please check the schedule on the website. We have a few more talks coming, and for people that are staying, we can definitely take a few more questions. So you can just unmute yourself or type the question in the chat. So there is one question by Satish, and he asks, is it possible that some clients have similar heterogeneity and some have very high heterogeneity? And is there some way to cluster these clients with different heterogeneity levels?
Yeah, that's an excellent question. I have not worked in that topic, but I know Martin Yerke's group has done some work there. I think Sebastian might be familiar, like where they tried to identify these clusters where you can apply personalization. And there is indeed work in trying to first do some sort of clustering and then try to do personalized learning on top of that. Although I should mention that if the server is doing the clustering, that is one thing, but you don't want the clients to form collusions when you are dealing with data, because that can be potentially harmful to the health of collaboration. But yeah, I think that's a very interesting direction. And yeah, some of this theory might be relevant to understanding algorithms like that.
Okay, so Daniil has a question. Yeah, you can just unmute and.
Yeah, so you showed that local SGD converges to the averages of solutions, right? In case when the step size is constant.
Right. But K goes to infinity. Like
Yeah.
So
but this is the case when we have unique solutions. What happened when we don't have unique solutions, let's say in convex optimization? Like what is the behavior of local SGD?
Yeah, that's a great question. So unfortunately, the closed form I wrote for fixed points can only be written when we have like simple quadratic strongly convex problems. But I do have some intuition what happens when the problems are general convex. You can have two things. One is that you don't converge at all. There's no actually point of convergence. That can certainly happen. And if there is some nice property like there's a shared optimum between these general convex problems, like these general convex problems might have several optima, and these sublevel sets of their optima might not have an intersection, but they might be close to each other. Like there might be some point which is like good enough for both of them. And my intuition is that local SGD should recover some point which is close to both these sublevel sets, but it might not in several settings because there are pathologies which can push local SGD into like infinite directions which are like orthogonal to this point that we want to recover. But yeah, theoretically, I'm personally at least trying to understand what happens in the general convex setting with regard to fixed points. Yeah, I'm happy to chat more offline if you have more things.
Yeah, thanks. Thank you.
Okay, Anirban. Okay. So the easy thing to say about client subsampling is whatever I said in this talk. If you add client subsampling on top of that, it makes the job even harder for local SGD. Like for instance, like we have some work which is not published yet, which is looking at the variance induced by sampling from the clients. And you can think of some meta distribution over the clients, and then you're sampling from this meta distribution at each time step. And then there's an additional variance which is caused by this sampling. Let's say that variance is controlled by zeta star as well, like because zeta star is essentially controlling the inter-client variance. So you might as well want to control the variance when you're sampling from the clients. It turns out that there's a noise term or heterogeneity term which you cannot get rid of with finite communication when you have client subsampling. You have to do infinite communication unless the zeta star is very small. So yeah, client subsampling definitely makes things hard. And while I've not looked at the convex setting yet, we do have some work in the non-convex setting where we did look at client subsampling. So let me share my screen again to show that. It is basically this paper. In this paper, we actually looked at client subsampling in the non-convex setting and how it affects local update algorithms. And yeah, it just makes the job harder. Like you can imagine that if I already have confusions about which directions my algorithm has information about, if I don't even know anymore which clients I'm going to sample, then it can happen that I can create these examples where these pathologies appear over time. And yeah, that is certainly challenging.